All right, we're diving back into this cosmic puzzle. Does quantum entanglement prove the holographic universe? Spoiler alert, it doesn't prove it, but it's like a tantalizing breadcrumb trail leading to some wild ideas about reality. Since you want a long clarification, I'm going to unpack this with all the juicy details quantum mechanics, holographic theories, and the buzz from X included. We'll keep it vivid, conversational, and maybe a bit weird, like we're riffing at a late night coffee shop. Let's go. Now, jumping into quantum entanglement, the spooky basics. Quantum entanglement is the rock star of quantum mechanics, the thing that makes physicists scratch their heads and go, what even is reality? Imagine two particles, say photons, getting linked in a special way. Once they're entangled, their properties, like spin or polarization, are tied together. Measure one, and bam, the other instantly snaps into a matching state, even if it's on the other side of the galaxy. It's like they're texting each other faster than light. But quantum rules say no actual message gets sent, so Einstein's speed limit isn't broken. This isn't sci-fi. It's been tested to death. Back in the 70s and 80s, folks like John Clauser and Alan Aspect ran experiments called Bell tests, showing entanglement can't be explained by classical ideas like hidden signals. In 2015, loophole-free tests sealed the deal, and by 2022, Aspect, Zeilinger, and Clauser nabbed a Nobel Prize for proving this stuff is real. On X, you'll see people call it quantum magic or proof we're in a simulation. But it's just quantum mechanics doing its weird thing. No matrix required, yet. Why's this matter for the holographic universe? Entanglement suggests the universe has a kind of non-locality. Information isn't stuck in one spot, but shared across space in ways that defy our 3D intuition. That's a big clue when we talk about holography, so let's get to that. But does quantum entanglement prove the holographic universe? A cosmic hologram? The holographic principle is one of those ideas that sounds like it was cooked up in a sci-fi writer's fever dream, but it's legit physics. It says that everything happening in a 3D volume of space, like, say, the entire universe, can be fully described by information encoded on a 2D surface surrounding it. Picture a hologram on your credit card. A flat surface projects a 3D image. Now imagine the universe working like that, where a 3D reality is a projection from a 2D screen at the edge of the cosmos. Mind-blowing, right? This idea came from black hole physics. In the 70s, Stephen Hawking showed black holes give off radiation and lose mass, which raised a problem. Where does the information about stuff that falls into a black hole go? Jacob Bekenstein suggested it's stored on the black hole's event horizon, its 2D boundary, not inside its 3D volume. The entropy, a measure of information, scales with the surface area, not the volume, which is weird for a 3D object. Fast forward to 1993, Gerard Houft and Leonard Susskind took this further, saying maybe the whole universe is like a hologram. The best evidence comes from a mathematical idea called the AD-CFT correspondence, cooked up by Juan Maldacena in 1997. It says a 3D universe with gravity, anti-de Sitter, or add space, is exactly equivalent to a 2D quantum field theory, CFT, on its boundary. It's like saying the 3D world you see is just a fancy shadow of a 2D code. Ex-posts love this. Some call it proof we're in a cosmic video game, though most physicists just say it's a cool math trick for now. No lizard coders confirmed yet. Now, where does entanglement fit? Here's where it gets spicy. Entanglement might be the key to making the holographic principle work. Let's break it down. 1. Non-locality vibes. Entanglement's instant correlations across vast distances scream non-locality. In a holographic universe, the 2D boundary encodes all the info for the 3D interior. That boundary has to have some funky, interconnected properties to pull it off, and entanglement fits the bill. On X, you'll see folks say entanglement's like the universe's Wi-Fi, which isn't totally wrong. 2. EREBER, wormholes and entanglement. In 2013, Susskind and Maldacena dropped a bombshell called EREBER. ER stands for Einstein-Rosen bridges, wormholes, and EPR is the famous Einstein-Podolsky-Rosen paper on entanglement. They suggested that two entangled particles might be connected by a microscopic wormhole in spacetime. If true, entanglement isn't just a quantum quirk, it's literally shaping the geometry of the universe. In a holographic model, these connections on the 2D boundary could create the 3D spacetime we live in. On X, people lose their minds over this, with some calling it proof spacetime's a quantum network. 3. Entanglement entropy and Ryu Takayanagi. There's this thing called entanglement entropy, which measures how much two quantum systems are entangled. In AD-CFT, a formula by Ryu and Takayanagi says the entanglement entropy of a region on the 2D boundary matches the area of a minimal surface in the 3D bulk. This is huge. It's like saying entanglement on the boundary creates the shape of spacetime inside. It's not proof we're in a hologram, but it's a deep hint that entanglement and holography are buddies. 4. Spacetime from entanglement. Physicists like Brian Swingle argue that entanglement might be the glue holding spacetime together. In a holographic universe, the more entangled the 2D boundary is, the more connected the 3D spacetime inside becomes. Some even say if you disentangled everything, spacetime itself might unravel. Yeah, don't try that at home. Now, here's the buzzkill. Entanglement doesn't prove the holographic universe. It's supportive, but we're not popping champagne yet. Here's why. 1. AD-CFT isn't our universe. The AD-CFT correspondence, the best holographic model we've got, works in anti-de Sitter spaces with negative curvature. Our universe, based on cosmic microwave background data, like from Planck in 2018, seems flat or slightly positively curved. We don't have a holographic model that perfectly fits our cosmos. X-posts often miss this, hyping AD-CFT as the answer when it's more like a toy model. 2. Entanglement's everywhere. Entanglement happens in labs, photons, atoms, even diamonds, without needing a holographic universe. It's just a feature of quantum mechanics. You don't need a 2D boundary to explain entangled particles in a lab in California. It's cool, but not hologram-specific. 3. No direct tests. The holographic principle is a theoretical idea, not something we can test directly yet. Entanglement's been confirmed in experiments, but there's no lab setup that says, yup, the universe is a hologram. Some folks on X point to cosmic microwave background anomalies as possible hints, but those are speculative at best, more, ooh, maybe, than case closed. 4. Other theories exist. Entanglement's weirdness could fit other frameworks, like loop quantum gravity or string theory, which don't lean on holography. The non-locality doesn't scream hologram, specifically. It just screams quantum mechanics is nuts. 5. Philosophical hurdles. The holographic idea messes with our sense of reality. If it's true, is spacetime real, or are we just shadows of a 2D code? Entanglement supports the math of holography, but it doesn't answer these big questions. On X, you'll see people tie this to simulation theory or even spiritual stuff, like we're all one, but that's more vibes than evidence. Now, what's the buzz on X and beyond? X is a goldmine for this topic. In 2025, posts range from hardcore physics nerds citing papers on entanglement entropy to wild threads claiming it's proof we're in a cosmic video game